Okay, so now we're going to discuss Hess's law, and this is the formula that we're going to use to calculate how much energy is being released through our heat of combustion. Hess's law can be used for any type of reaction, but for Science 30, we are going to look at just combustion. Okay, so if you turn to page 5 of your data booklet, you will see this formula. So delta C, H with a little circle, equals the sum of the number of moles times the standard heat of formation of our products minus, so we're going to bracket that, the sum of the number of moles times the standard heats of formation of the reactants. So basically what we're doing is we're adding up how much energy we have in our products, adding how much energy we have in our reactants, and we are going to subtract the two to find out the difference. Okay, so standard heats of formation, you're going to find these on page, that data table. The table, this is the table, it's down here on page 5 of your data booklet. Okay, it looks something like this. Okay, and you'll notice that we have negative and positive signs. So down here at the bottom, take a note right here. This is really good because it tells you some information here. Any element, so anything that's a pure element, so for example, oxygen gas is a pure element for us in combustion, it will have a value of 0 for its standard heat of formation. It tells you here also that the negative sign is exothermic and the positive sign is endothermic. So when you look at these reactions, so for example, if we take a look here at butane, it is negative 125.7. So that tells us that when we make butane, we actually release 125.7 kilojoules per mole of energy. Okay, so we're going to come back to this table and we're going to be using it in our formula. Okay, so let's try an example together. So we're going to calculate this heat of combustion for 1 mole of butane gas used in cigarette lighters. So the first thing we're going to have to do is write a balanced equation. So they give us the chemical formula, C4H10. We know it's combustion, so we're going to be using oxygen gas. And then the products are always going to be water, vapor, plus carbon dioxide gas. So now we got to balance our equation. So let's do our carbons first. So here I've got 4 carbons. So I'm going to put a 4 in front of my carbon dioxide. I've got 10 hydrogens. So I'm going to put a 5 in front of my water. And then I need to total up my oxygens. So for my water, I get 5 oxygens from water. And then I get 4 times 2 is 8 O's from carbon dioxide. So I'm going to end up with 13 oxygens. Okay, so again, normally we wouldn't leave this as a fraction 13 over 2, but because we're only calculating for 1 mole of butane, we're going to leave that as 13 over 2. Okay, so now in order to do the formula, we need to just set up kind of our information, and I like making a table just because it keeps everything organized. Okay, so one thing that we need for our formula, if we go back here, is we need number of moles, and we need the heat of formation. So I'm going to set up 2 rows for that on my table here. So the first one is number of moles. And that is simply the number in front of the compound. So there's no number here, so that's 1. Oxygen, there's 13.5 moles. Water, we have 5. Carbon dioxide, we have 4. Okay. The next thing we need for the formula now is the standard heat of formation, and this is in kilojoules per mole. So you'll notice that when we start multiplying, we're going to cancel out those moles. So now we go back to our table on page 5, and we're going to look up butane. So here's our butane. Its heat of formation is negative 125.7. So I'm now going to add that into my table. So negative 125.7 kilojoules per mole. Oxygen is an element, so it is 0. Water vapor we go back to our table, is all the way down here. It's a gas. Negative 241.8. Negative 241.8. And then if we go back and take a look at carbon dioxide's up here, negative 393.5. So negative 393.5 kilojoules per mole. Now we need to plug it into our equation. So remember, the heat of combustion, or really any reaction, is the sum of N times the standard heats of formation of the reactants. Subtract from that the sum of N times the standard heat of formation of our product. Sorry, I did that backwards. This should be products. Products go first, and reactants. Let's just double check that we wrote that properly here. Yeah, products minus reactants, good. Okay, so now what does that mean? So we're going to start with the products first. I'm looking at these values over here. So what I'm going to do is I'm going to multiply the number of moles, so I have 5 moles of water, times the standard heat of formation for water, which is negative 241.8, and I'm going to add to it 4 times negative 393.5, and that's going to be this, and I'm going to add that up, that's the sum of my products. So over here I'm going to get 5 times negative 241.8 plus 4 times negative 393.5. That's my first sum. Then I'm going to take a look over here. I'm going to look at my reactants. 1 times 125.7 negative plus 13.5 times 2. So this is going to be 1 times negative 125.7 plus 13 halves times 0. Okay. When you plug that all into your calculator, you should get negative 2,783, and subtract from that a negative 125.7. So our final answer in terms of heat of combustion, before we round it, is negative 2,657.3 kilojoules. And we always want to round to 3 digits, especially if we're doing a numerical response. So our final answer for our heat of combustion is going to be negative 2.66 times 10 to the 123 kilojoules. And that would be our final answer. Okay. Let's try one more example, and then I'll let you do some on your own. Okay, so this next one is, what is the heat of combustion of 1 mole of methane? So again, if you don't remember the chemical formula for methane, we can always go back to our table here and look at methane. Here it is, or here it is, and there's the chemical formula. Okay, so let's start out by writing out our balanced equation. So CH4 is a gas, plus O2, remember methane is natural gas, will produce water, vapor, plus carbon dioxide gas. So again, number of moles and standard heats of formation. And this is going to be kilojoules per mole. And we're just going to balance our equation first. 1 carbon, 1 carbon. 4 hydrogens. We need 2 waters. That means I've got two oxygens here, plus 2 oxygens from carbon dioxide, so 4. So I need a 2 in front of my oxygen, and we're balanced. So number of moles, methane 1, oxygen 2, water 2, carbon dioxide 1. Okay, standard heats of formation. So go back to our table, look at methane, negative 71.6, negative 71.6. Oxygen's always 0. Water is 241.8, and carbon dioxide is negative 393.5. Okay, let's plug it into our equation. The heat of combustion is the sum of N times the standard heat of formation of the products minus the sum of N times the standard heat of formation of the reactants. Okay, whoops. I'll bracket those up. So let's take a look here again. Remember, here are the products. We're going to multiply them, and then we're going to add them. Okay, so it becomes 2 times negative 241.8 plus 1 times negative 393.5. Then we're going to subtract from that the reactants. So 2 times 71.6 plus 2 times 0. So 1 times negative 71.6 plus 2 times 0, which is now going to equal, if you do all the math in your calculator, 802.5 kilojoules. And if we have to round it, it'll be 803 or negative 803 kilojoules. So if you don't get that negative number, because that tells us it's exothermic, whoops, exothermic, something went wrong. So if you get a positive number, you did something wrong and you should retry it. Okay, so there are some practice problems in your textbook you can do. These are on page 498. The answers will be in the back of your textbook, which will give you some help. And then as well, in your work booklet, if you picked up the work booklet, you will have this worksheet. You don't have to do number 1 because we've already done that, and there's an answer key for it as well. Okay, good luck, and if you have any questions, make sure you email me, and we'll come back and we'll start talking about efficiency.